Okay. Little chit chat about the end of the semester before we get into stuff. Reminder, next Friday, last day for later missing assignments. Okay, so plan on completing things. That's the last day. Remember, there are two homework drops that happen automatically. So like if you got 2 missings, like it's fine. They're gonna get dropped anyways. You don't have to scramble to finish that stuff or whatever. They automatically update, so as you complete things, like the drop will move to the next, to be maximally advantageous to you automatically. There's the survey in my Notre Dame at the very bottom under the announcements, letting me know whether you want to take a double high test score, do a test retake. You guys have everything is done, so you should be able to make that decision. If you haven't filled that thing out, try to find some time to do that here in the next 24 hours, ideally. Particularly if you're planning on doing a retake, so I have time to get an extra version together and get that where it needs to be for your retake. I think is that okay? Everybody feel good on that stuff? I think we mentioned all these things already, but it helps to reiterate because people are coming and going. So the exam format, I am still working on putting the finishing touches on this, but the format is the format. So you're going to have 5 different types of problems. You have multiple choice questions, limit problems, derivative problems, definition or theorem problems, and then application problems. Inside of each of those sets of problems, there'll be 10 to 20 points worth of questions. For each section, the maximum score you can get is 10, so everything is graded out of 10 points. So you can get 50% of 20 points and get the max score if there was 20 points in the section. You can't carry points from one section over though, so the max score you can get in a section is 10 points. Even if you get 20 out of 10. It doesn't help you any more than 10 out of 10. Is everybody okay there? And I'm still kind of updating and putting finishing touches on that. I've been swamped getting that done, but I think we talked a little bit about this last time, though, didn't we already? Once I have everything locked, I'll tell you exactly the number of questions and stuff inside of each section or whatever. I don't know that it'll really make much of a difference to you, but just being honest at where we're at. Everybody okay? All right. Last topic for this semester is going to be optimization. Next class, we'll do I have some in-class practice for related rates, optimization, and these first and second derivative test kind of problems that you will just work on in class or whatever. And then after that, you can, just exam review time. Sound good? Fair warning, optimization tends to be a pretty difficult topic for students in the same way that the related rates problem are difficult for students. Not because the calculus pieces are difficult, but rather because the setup is difficult, because you have to read and draw pictures and label things and create equations and sometimes you have to eliminate variables and that's the part that tends to be hard for students. It's just the pre-algebra skill part of it. I know, you're well, it is hard. So just for the related rates, our textbook gives us a suggested plan of attack to deal with these kinds of problems. So step 1 is understand the problem. First step is to read the problem carefully until it is clearly understood. That may mean that you have to read the thing 2 times, 3 times, 4 times, so you have a good picture of kind of what's happening in your mind. Ask yourself, what is the unknown? What are the quantities? What are the given conditions? Often, what are we trying to maximize or minimize if it's an optimization question? And what is the parameter that that we need to change in order to find that maximum minimum value. Step 2 is to draw a diagram. I would say that 2/3 or more of these optimization style questions have a geometric component to it. So drawing a picture can be really helpful. When you do that, you should label things and include the givens and that sort of stuff. Step 3 is to introduce notation. So first thing you want to do is assign a symbol to the quantity that we're trying to maximize or minimize. In this particular example, the textbook's going to use the letter Q. But you also want to select other symbols for other unknown quantities and label our diagram with these symbols. And they give us the super helpful hint of like, use suggestive symbols like A for area or H for height. Gee, I would have never thought about that. I'm being sarcastic there. Step 4 is to express Q in terms of some of the other symbols from step 3. Really, you're writing an equation at that step. Tends to be a hard one. Step 5, it says if Q is expressed as a function of more than one other variable, use the given information to find relationships in the form of equations among these variables. Then, use these equations to eliminate all but one of the variables in the expression of Q. Thus, Q will be expressed as a function of one variable. This is very much what we have to do in related rates, right? Where you have to those cone questions, oftentimes you had to use that similar triangles equation to eliminate an H or an R from it so that we could differentiate. The last sentence of 5 is the most common mistake students make. The last sentence says, write down the domain of this function. Why is that going to be important? Because if we're looking to find the absolute maxima or minima for a function, the technique we'll use is going to be different if we're on a closed interval or if we're on an open interval. So we absolutely need the domain before we can proceed into step 6 or to be able to finish step 6 correctly. Step 6 says use the methods from sections 4.1 and 4.3 to find the absolute maximum or minimum value for our function of Q, or function for Q, I should say. In particular, if the domain is a closed interval, then the closed interval method from section 4.1 can be used. If it's an open interval, it tends to be a little trickier. We'll see an example there, and that we actually get an update to our open interval procedure inside of this section. It'll cover special cases that make it a little bit easier. How do you guys feel on this procedure? We'll walk through several examples now, but notice that there's no new content happening here, right? It's just like, here's an application. All the tools that we need to do this, you have at your disposal. Okay, along the way, we're gonna update one of them to make the process a little bit simpler in a special case, but for the most part, we have everything we need already. All right. The first question says, a farmer has 1,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field, or what are the dimensions of the field that has the largest area? Take a moment, read that again if you feel like you need to understand what's going on. Is anybody unclear as to what we're trying to do here? Okay, well, let's draw a picture to kind of summarize what's happening. So here's my river. There's my rectangular area. So I'm going to call that A. We want to maximize A. Everybody's so far so good. When we talk about a rectangle and we talk about its area, what are the two measurements that we need to, or that we typically care about? Length and width. So I'm going to label sides as either L or W. Does it matter how I label them? No, right? You could have labeled the two sides W's and the other side L. You get an equivalent answer. It doesn't really matter. Everybody so far so good? Okay. And it tells us we have this one other piece there that we have 1,400 meter or 2,400 feet of fencing. What does that mean? Excellent. If I add up that perimeter, I should get 2,400 feet or 2,400 feet of fencing. Does everybody feel good? Okay. We made one little assumption here that I don't think is much of a leap. Does anybody see what it is?
We actually don't. We made an assumption that like wasn't given to us.
It wasn't expressly said, but I think common sense would dictate that it's okay to make this assumption. Meredith?
Like the length are going to be the same. Because...
Well, the two L's are going to be the same because it says it's a straight river.
Oh,
right?
okay.
You can assume that. That's okay. No, the assumption that we made is that the biggest area possible, we'll use all of our available fencing. Now, in common sense terms, that should be like, of course, that's how that has to work. You guys all agree? Now, in different situations, using everything you may not need to use everything to get the optimal, right? But in this particular case, I think that's pretty clear that that's got to be what happens, right? Okay. All right. So we're through step 2 now. Everybody agree? Step 3 says we want to write an equation for the quantity that's being maximized. What is the quantity being maximized? Area. So my equation for area should be A equals length times width. Both of those are variables, correct? So my equation for area is in 2 variables. That will not work for us. We need it in terms of 1 variable. So we need to rewrite this in terms of either L or in terms of W. How are we going to do that?
Just divide by subtract by 2.
We're going to use this other equation and make a substitution. Just like we would in a related rates problem. If we have too many variables, we need to find another equation and make a substitution. Okay? Should it matter whether I substitute so that I have all L's or all W's?
No.
No. Which one should I choose, though? Let's choose to substitute so that we have all L's by replacing the W, I think is what you're trying to say, right? Why would I choose to do that? Yeah, there's no fraction involved, right? If this is going to be a potentially by hand problem, I do no thank you to fractions if I don't have to. So now we have an equation in terms of L. So far, so good? So we're into step 5 now, right? What's the last part of step 5 that I warned you that was going to be the one that students forget? The domain. Okay. So what is the smallest value of L that should be possible here? You have to think about this in the context of the real world. 0, right? Why 0?
Because you can't have negative.
You can't have negative length. L is the length of something, right? What's the biggest possible value of L that I could have? What's that?
2400.
Nope, 2400 will give me a negative area. But you're close.
Should divide by 20 by 3.
Not by 3,
2.
by 2. Why 2?
There's 2 variables.
Right? If I do 2 times 1200, what do I get? 2400. 2400 minus 2400 is 0. That's the smallest area I can have, right? If I get any bigger length than that, I'll have a negative area. Everybody's okay? So far, so good? We're into step 6 now, which is just using our methods from 4.1 or 4.3 to find the absolute maximum or minimum. In this case, it's an absolute maximum, because it told us to find the maximum of the problem. What type of interval am I finding the absolute maximum on? Is it open or closed? Closed, because it's or equal to, right? 0 area is fine, so we'll do this as a closed interval. To do that, I need to evaluate what things? What things do I need to check to find the absolute maximum on a closed interval? I need to check the critical values and the endpoints. Okay? So I need to check the critical values and the endpoints of my interval. Ready so far, so good? What is a critical value again, Mr. Kulak?
Anything that doesn't equal, well, anything that equals 0 or undefined.
Okay. That's anything that what equals 0 or undefined?
Valid.
The derivative. The derivative. So we need a prime here first. What should we do to find a prime of L?
Take the derivative of the A of L.
Okay. To do, what do we have to do that?
Distribute the L's.
Ah, that's what I wanted you to say, yes. So before we take the derivative, let's distribute that L through. Why would I want to do that?
So there's no chain.
Not a chain rule, but a
Product.
product rule, yes. It avoids having to do a product rule there when we do the derivative. That's very good. What's the derivative of 2400L minus 2L squared?
2400 minus 4L.
Good. So, now that I have that, we'll find where that derivative is either equal to 0 or undefined. Let's start with the undefined piece. That's the one you guys are most apt to skip because so often there's not a value. Where is the derivative undefined? Nowhere. Why?
It's a polynomial.
It's a polynomial. Okay, good. Okay, and where is it going to be equal to 0 at?
Whatever 24 and 600.
600, right? 2400 divided by 4. Is it okay that I just write down the number? I feel like at this level you guys are good with that. Skip a little bit of trivial calculation. Okay. Now it's time to check. When we check, do we check with F or F prime? F. Or in this case, A. What's the other one? Oh, 1200. That was the other one. Guess what? Those ones we already did, right? When we finding the domain, we did that automatically. Uh, 72 with 4 zeros after it, I think, right? I don't know, that was me mental math, right? 600 times 1200, 6 times 12 is 72, and then should be 4 zeros at the end.
Why are you trying to find A of 1200 as well?
Those are the endpoints of my domain. 600 was the critical value. Okay, so what does this tell me? That's my maximum area. What did the question ask for, though? The dimensions. So we know the L is 600. What is the W going to be? How about I just use 2400 minus 2L? Everybody agree? Which is, again, 1200. I heard somebody whispering. I think it was Mark. So those are my dimensions. Does that feel okay? The calculus piece? Fairly easy, right? Doing the first and second derivative test and doing these finding maxims and mins is typically the easy part. What was the hardest part? Yeah, getting that equation for A to a single variable would have been the hardest part of this, right? Once you got there, though, it was pretty downhill. All right. Gonna need more space than this. A cylindrical can is to be made to hold 1 liter of oil. Find the dimension that will minimize the cost of the metal to manufacture the can.
So it almost not a metal.
Yes, because we can assume the more metal we have to use, the more expensive it's going to be. I think it's a fair assumption. Everybody agree with that? If you buy more of something, typically it doesn't get cheaper. Maybe the rate, but the actual bill doesn't get cheaper. Unless you find like a value plan at when you're at McDonald's or something. Okay. Does everybody feel clear as to like what's going on here? Okay. Let's draw a picture. There's my cylinder. What are the dimensions of interest on a cylinder? Particularly if we're talking about the amount of liquid it can hold. Height. And radius. And we're told the volume is 1 liter. What are we trying to minimize, though? Yeah, what is that going to be? What geometric measurement is the amount of metal going to be? Surface area. Yes. Excellent. Everybody's okay? Now, there's one other thing that I would deal with right now that our textbook loves to do this. It is not common on the AP, but our textbook loves to do crap like this, and it just annoys the bejesus out of me. Does anybody see what I'm going to complain about? We have a units problem going to be happening here. What is the problem? We're looking for an area, right? But the volume is given in liters, right? What will the area be given in? Like square inches or square feet or square centimeters or something. You see what the problem's going to be here? We have a unit problem if we're going to start like dividing these things. So I want to rewrite 1 liter so that it's like a cubic unit of length. Does anybody remember the conversion factor between meters and cubic units of length? How much is 1 cubic centimeter? You got like 1 cubic centimeter, like a little tiny box, like this big. It's 1 milliliter. Is 1 cubic centimeter. If you think about that physically, like a milliliter is like a drop. Like if I take the drop and put it in like a little tiny cube, that's about what would fit in there, right? So 1 liter is going to be 1,000 cubic centimeters. Sorry, did I say milliliter before? Yes, that's right. 1 milliliter is 1 cubic centimeter. Yes. It's like, milliliter or millimeter? That makes a big ding-dong difference. Anyway, so that's going to be fine. So now my answers will my lengths and areas will be in terms of centimeters or centimeters squared, which is good. Now, I don't see the AP doing stuff like this very often. Our textbook will do this to you all the time. So as you're doing the homework, you're like, what's going on with these units? This is not working. Probably something like this. Which I know is like real irritating. It's like, these problems are hard enough. I don't need like a unit conversion stuck in here. Especially one like this where it's like, I don't know that I remembered that. If you're a professional chemist before, you would remember this. Okay. I think we're on to step 3, right? We need to write our surface area equation. Who remembers this? I didn't think so. All right. If I take my cylinder and I like cut it out and unfold it, what are the 3 shapes that I'm left with?
2 circles and a rectangle.
2 circles and a rectangle. Wonderful. What's the area for a circle? Not 2 pi r. That's perimeter or circumference. Pi r squared. So we have 2 pi r squared for the 2 circles. And what's the area for a rectangle?
Length times width.
Length times width. But we don't want to use length times width. We want to use r and h, right? So what is the height of our cylinder is the same as like the width of our rectangle, right? What will the length be? Yeah, so if I cut out this cylinder like I snip here, that's going to be like the top length, right? That's our circumference. So there we go. Everybody happy with what we did there? Okay. What's the problem? That's not so much the problem. We have 2 variables, surface areas in terms of R and H. How many variables does it need to be in terms of? 1. So what are we going to have to do? We have to do some kind of elimination to substitute out either R or H, so it's in terms of just 1 variable. Ideally, which variable would we be shooting for? Probably get rid of the H, right? Since there's only 1 of them and it's not squared. What other thing do we know about that we could write another equation with? The volume, yeah. Who remembers the volume for a cylinder? It's the area of the base, pi r squared, times the height. And now I really want to get the h by itself because I don't want to mess with the square root at all, right? If I try to get the r by itself, I have to square root both sides and like, no thank you, pass on that, please. So h would be 1,000 divided by pi r squared. Everybody see it? What I did? Okay. So we'll eliminate the h now. What do you notice that we can also do? Oh my gosh. Guys, forgot to write that r. Do that. Everybody feel good there? Clean up. That's pretty good. Let me rewrite this now. And I'm going to write it that way. Why did I write it that way?
Why do you still have an R?
It was an r squared in the bottom.
Oh, okay.
It just was a messy squared.
Okay.
Sorry.
It's okay.
My penmanship. Ah! Why do you suppose I wrote it with r negative 1 instead of 2,000 over r? Yeah, it's going to make it easier to take the derivative of. But before we take the derivative, what do we still need to do? I told you guys were going to forget to do it.
Domain.
The domain, yeah. All right. So r is the thing that's our independent variable. What's the smallest possible value of r that we can have?
0.
Well, it can't be 0. Why can't it be 0?
Then that's not even a circle.
No.
Okay.
Where is the r at? There's an r in the denominator. Can I have 0 in the denominator of my function? No. So it can't be 0, but it can be right up to 0. Everybody agree?
So the question about the length and width, you can have length 0.
Yes. Because if you go and just look at the function, there's no reason that 0 length gives you an unreasonable area, right? It just gives you an area of 0, so you contain nothing. But that's fine. That's feasible, right? Like nothing is something. Sort of. But if I have a 0 radius now, my denominator is undefined. This has no output. No number comes out of this. Not even like a weird number, right? Before, like negatives, obviously that's bonkers, right? You can't have negative areas coming out. But here you can't have 0 radius because it's going to make the function undefined. Is there a biggest possible value for r?
No.
No, right? Even if I think back to here, like if r gets as big as I want, it just h goes to 0, but it's never going to get to exactly 0, right? So, we have like an open interval going on here. We haven't exactly talked about how to deal with this and finding an absolute maximum or minimum, but we will in a second, okay? And it's nothing that we need that's beyond our capabilities. Nothing new that we need, anyway. Everybody's good so far? And I guess I should write this like SA of R, since we're down to we have a function of one variable now. Okay, what do we do next? Yeah, we need to take the derivative. We need those critical values, right? Now, we don't need the endpoints because this is an open interval. Instead of the endpoints, we need to check the limit at the endpoints. So the critical values, I need the derivative of the surface area. What's the derivative of 2 pi r squared?
4 pi r.
4 pi r. What's the derivative of 2,000 r to the negative 1?
2001 over 2000 r squared.
Negative 2,000, yeah. And I'm still going to write it with the negative exponent. I just think it's easier. So everybody's good with the derivative there? Okay. And now we'll set this thing equal to 0 and look at where it's undefined. And where does the derivative fail to exist?
0.
0.
Anything less than 0.
Anything less than 0 is, well, I mean, sure, that's not a feasible value for r. But does r equal 0 matter to us? No. Why not? It's not in the domain of f, right? If it's not in the domain of f, it's surely not going to be in the domain of the derivative anyway. So, like, doesn't matter. Still none coming from there. So don't be tricked by that, right? You probably would have caught it when you drew it to test it and you got undefined. All right, how do we solve this equal to 0? Guys, how do we solve that when it's equal to 0? Whole out, well, one r is a positive exponent, the other is a negative exponent. What's the problem? Why the hesitation, guys? What's hard about this? The negative exponent? Well, let's make it not negative. What do I multiply both sides to make that exponent not negative? Yeah. Is it okay to do that? Definitely is. How about now? Does that look doable now? What do we do? And then? Okay, and then? Okay. So r is going to be the cube root of 2,000 divided by 4 is 500. And then I'm going to reduce this radical. Cube root of 500, what can I take out?
No.
More than 5. 10, right? Right, no. No. No, I'm wrong. No, this is good where it is. Okay, that's fine. All right. So far, so good? Okay. So now we'll do our check. We need the limit as x, or I should say r approaches 0 of SA of r. I'll just write it out, it'll be easier. What's that? I'm going to write it this way. I'm gonna need SA of and then I would need the limit as r approaches positive infinity of this guy. Is everybody okay here? Okay. Limit as r approaches 0 of 2 pi r squared. Limit as r approaches 0 of 2 pi r squared. Just the first chunk.
0.
0. Okay. The limit as r approaches 0 of 2,000 over r.
Undefined.
Well, infinity.
Infinity is out. Undefined is not wrong, but infinity is the way we'd want to write it. How do you know it's positive infinity, not negative infinity?
Because as the number gets smaller, that number gets bigger.
Yeah, well, it's also because r has to be coming to 0 from the positive side,
Yeah.
right? Because our domain is such. So I probably should have done that, but you got the right answer, which is definitely matters, right? You did it.
Yeah.
All right. And then here, what do we do here? We just plug stuff in and it's nasty and gross and whatever. Okay. Yuck. Let's do the other limit now. What's the limit as r approaches infinity of 2 pi r squared? Mm-hmm. And what's the limit as r approaches infinity of 2,000 over r?
Negative.
Not negative. Frankie, what did you say?
0.
0 is the right answer. Why is it 0, Frankie?
Because it keeps getting smaller and smaller.
Yeah, heads towards 0, right? If you think about like the sequence, like 1/2, 1/3, 1/4, 1/5, you're going 0.5, 0.33, 0.25, 0.2, you're getting closer and closer to 0 as that denominator gets bigger. Okay, which of these three values is the smallest? Infinity, this thing, or infinity?
That thing.
That thing, right? What don't we know, though? We don't know if that's a maximum or minimum. Because this was a open interval, not a closed interval. What do we still need to check? We need to check the sign of the derivative before and after this. Right? Okay. What's the value between 0 and the cube root of 500 over pi with no calculator? Any value in between those.
1.
You say 1, are you sure?
That would be my guess.
Okay. 500 divided by 3 is 150-ish. The cube root of 150-ish is bigger than 1, right?
Yeah.
Okay. Give me a value now bigger than cube root of 500. 500, sure. I would just do 10, right? Because the cube root of 1,000 is 10. 500 divided by pi is definitely smaller than 1,000. Let's do that.
It's true.
Is that okay with you guys? Again, like, what you described, what did you say? 1,000 or something?
500.
500 would be fine, but like, kind of gonna, it'd be fine. I just wanted to point out to you, like, that's the way I thought about it. I'm like, 10 looks like a good number to me. So now I'll take the derivative and evaluate it at 1, the derivative evaluated at 10, but I don't actually care what the number is, right? What do I care about? The sign, whether it's positive or negative. So if I go back to the derivative, 4 pi times 1 cubed, oh, sorry, this is the derivative. 4 pi times 1 minus 2,000 over 1 squared. Positive or negative? Right, it's basically 4 pi minus 2,000. Yeah, that's negative. And if I plug the 10 in, I have 40 pi, right, which is like 120. And then 20 divided by 10 squared, or 2,000 divided by 100 is 20. 40 pi minus 20 is positive. If we're going from decreasing to increasing, we have a minimum. Whew. So this is my absolute minimum. What did the question actually ask for, though? Because that's the radius of the can that gives us the absolute minimum. What is it actually asking for in the question? Oh, find the dimensions. So we have the R. To get the H, we just plug in, and I'm not going to bother writing it down because the number, like, it's just gross looking, right? You'd use a calculator. Ideally, this is a calculator problem, but I think it's important that we should talk about how to do it with no calculator still, because having some number sense is important. Like, that's really helpful and time saving if you can just be like, all I need is close enough. Give me something that's a good estimate for this and just see what's going to happen. You know what I mean, guys? Okay. Now, what was the worst part about this? All of this like extra crapola that we usually don't have to do, right? That stunk. Guess what? What would you say if I told you under certain circumstances you can cut out having to do those limits and do that first derivative test to see whether you got a maximum minimum? Be like, cool, you have my attention now, because if I don't have to do that every single time, I would very much like that. And this is the workaround. So if I have a single critical value, and the derivative before that critical value is always positive, and after that critical value it's always negative, then what you have is an absolute maximum. Likewise, if it before the critical value were always negative and after you're always positive, then you have an absolute minimum. This works on an open interval. It allows you to get away without having to do the limits and an additional derivative test, which is nice, right? All that's required is that you have just a single critical value, which is often the case on an open interval. Does that feel okay? We'll do one more example, and then you guys are already looking pretty cooked today, so we'll do one more and we're calling quits. Like, I get it. I'm going to go down and do, I want to do this one because it's a non-geometric situation, right? We haven't seen one that didn't have like a picture associated with it. This is probably the next most common presentation, is where you have some kind of business-oriented problem. Because in terms of like continuous optimization problems, those are the two main places where you'll do optimization, is in some sort of manufacturing, like find the cheapest way to make this thing. And then in business, where it's like, find the amount of stuff that we should sell to maximize our profit or minimize our expenses or whatever. You know, how many employees do I need to like, you know, the most employees that I need to maximize my profit or whatever. How much do I need to sell or, you know, like whatever. You guys get the idea, right? It's not hard to imagine this being a very common corporate question. It's talking about like how much of this stuff do we need to make? I remember having like, we had like old green and black screen Apple computer, and there's a game on it called like Lemonade Stand or whatever, and you got to pick like, you know, they gave you the weather report, and then you had to pick like, hey, how much lemonade should I make? Like how many glasses should I make, and how much should I charge per glass? And your goal was to just try to make as much money, and there's like no end to it. But this as a kid was one of those where it's like, I wonder if it's better to make like 10 glasses when it's like hot and dry and just charge $10 a glass than it would be to make like 1,000 glasses and charge like 10 cents a glass or whatever. They had like a cost function built in. It was like this is what computer games looked like when I was a kid. And then like Mario Brothers came out like 2 years later and nobody did this kind of thing ever again. All right. As in a total aside now, you guys can remember my lemonade stand question. A store has been selling 200 Blu-ray disc players a week at $350 each. A market survey indicates that for each $10 rebate offered to buyers, the number of units sold will increase by 20 a week. Find the demand function and the revenue function. How large a rebate should the store offer to maximize its revenue? Considerably different sounding question than before, right? This one is probably harder to conceptualize because it's not like a physical shape, right? Read that again. Read it again. And just try to think about what's going on. So like a sale, like if you reduce the price by $10, you sell 20 more of these things. Does that make sense? It's like a coupon.
Yeah.
I mean, it is. All right. So what are we trying to maximize?
Profit.
Well, it says revenue. Since we don't know how much it costs to manufacture, or how much it costs to get these DVD players, we can't actually do profit. But we can maximize revenue. What is the parameter that we're changing in order to maximize revenue?
The rebate.
Okay, it would be the size of the rebate. In particular, I'm going to say X is the number of $10 rebates. So I'm going to have X just to be like a factor of 10, right? So if X is 2, we offered $20 of rebates. If X is 10, we offered $100 in rebate. Is everybody okay? All right, and then it gives us a hint. It says, write a demand function. Yes, Noah?
Is it asking how many rebates or how much the rebate should be?
Well, if we know the number of $10 rebates, then we can just take our answer, multiply it by 10, and that's the size of the rebate,
Oh,
right?
okay.
Is that okay?
Yeah, I thought it was talking about like the size of the individual rebates.
Oh, it's just going to be like one rebate, and we're going to have ours scaled by 10.
Okay.
I think is going to make this the cleanest to do when I read this. The demand function, right? What is the demand if the rebate is $0? 200 is the answer, right? Why? It told us in the start, right? And then if I offer one $10 rebate, how many additional players should I sell? 20. So this should be plus 20x, right? Everybody's good with that? Okay. What is revenue?
Total income
Total income. How am I going to calculate that?
and amount of array distance players who sell.
Times the price you're selling them for. Everybody's good with that? So my price is changing, right? If I offer 0 rebates, what is my price? $3.50, right? And is that cost going up or down? Is that price going up or down? Down, so I have minus. And then 10x, perfect, yes. And the number of units sold is just our demand function, right? So here's our revenue function and our demand function, our revenue function. Does everybody feel good here? Is that in terms of one variable? Yeah, that's kind of why I wrote X as like the number of $10 rebates, is because that allows me to like skip through having to do a substitution later on. And I think that them hinting to write the demand function and the revenue function also like help skip through some of that. Okay, what's my domain? Well, I wouldn't imagine that the rebate could be negative, right?
Question,
Sure.
if X is the number of $10 rebates,
Mhm.
then wouldn't you not have to multiply by 10 again?
So if we're giving 2.5 $10 rebates, how much are we giving off? $25. You have to multiply it by 10.
Okay,
Does that?
yeah, that makes sense.
Okay.
Yeah.
You're good?
Yeah.
Okay. I think just my verbiage probably was not
That
clear.
makes sense.
Okay. Brooks.
How did you figure out 200 plus 20x is the number of units sold? I thought it was gonna be like, I thought the whole thing to figure it out was gonna be, yeah, scroll a bit, it was gonna be 350 times 200.
For every $10 rebate, you sell 20 more players.
Oh, never mind, okay, thank you.
Yep. Okay. Domain for this. What's the smallest possible rebate you can offer?
0.
0, right? You just keep doing what you're doing. What's the biggest possible rebate you can offer? Not 350, 35, right? Because the biggest discount you can give is to just give the things away. Their cost is 0.
That'd be pretty cool.
Yeah, be a pretty bad business plan, I think. I don't think that's going to maximize revenue for you, but
Why are you dividing 350 by 10?
because if X is 35, 350, or 35 times 10 is 350. Is that, you got it? We're good? Are we ready to differentiate? Yeah, what would I do? I would do something first. I'd FOIL it out, right? Because I don't want to do the product rule on this. I could, it's not that bad, but like, Do you want to do it?
70,000.
70 with 4 zeros after, I think.
Wow.
700. And then I have a 7,000 minus a 2,000, yeah. 700 times, yeah,
Oh, okay.
that looks good. Oops. So if I take the derivative, this guy goes bye-bye. That just becomes 5,000 minus 400.
Why is this accepted?
Oh. Thank you. Very good. So far, so good? So equal to 0, I get x is, what is it? It's 50 divided by 4. Or what's that? 12.5? Why are there no places where the derivative is undefined? Wonderful. All right. So then we just do our closed interval check. Thankfully, those two are done for me. And I know that this is going to be greater than 0. I can tell that just by looking at it, right? 350 minus 10 times 12.5 is 350 minus 125. And then 12 or 20 times 12.5 is, well, it's positive anyway, right? So like, I don't care what the number actually is because it doesn't ask me for the revenue.
This
right?
is the test to figure out if there's a place on the interval where like prime of x is equal to 0.
Well, because it's a closed interval, all I need to do is check to see which one of these, the endpoints or the critical value, gives me the biggest output.
So that'll be the middle one. Then.
That'll be the middle one. So that tells me the absolute maximum occurs when x equals 12.5, which is $125 discount. Which is bigger than I thought. It's a big discount. That's why we can give some, it feels like you're giving this stuff away sometimes, right? It's like, well, maximize our revenue here, move some units. This feels like a good stopping place. Actually, it felt like a good stopping place, the question before this, but I wanted to do one where there was no picture, because I feel like that's an important idea. What'd you guys think? It's all right?
The second part was like,
Yeah. Well, the second one would be easier if you had the open interval method that we had described, where you don't have to worry about the limits and stuff. You just like, oh yeah, it doesn't matter. All I do is just do like a first derivative test and just, if there's only one critical value, and I'm done. He was how you guys feeling? It's all right? Life's okay? All right.